In this video, we're going to be talking about airflow, we're going to talk about static pressures, and we're going to talk about air conditioning troubleshooting. And I've titled this video, When It Won't Work. Okay, I've titled it that way for a reason, and the reason is simply that if you don't have good airflow, no matter what you as a technician or you as a homeowner do to the system, it's just not going to work. Replace the system, whatever, but it's not going to work. Okay, to make sure we're all on the same page, let's talk about some air handler basics. Okay, if we're looking at a horizontal air handler, that's one that might be installed in an attic or a crawl space on its side. We have a return plenum, we have the air handler, and we have the supply plenum. All the ductwork is connected to either side of this. In the return plenum someplace or on the return side of the ductwork, we have an air filter. Then we go into an indoor coil. Then we have our blower. We might have heat strips or some other means of heating. And then we have a supply plenum. Okay, so this is what makes up our air handler in a horizontal mode. The air, most often, 99% of the time, moves from the return plenum through the indoor coil, through the blower, across the heat strips, and out the supply plenum. Now, in some older systems, the indoor coil and the heat strips may all be on the what I call the supply side or the positive side of the system. Okay, but 99.9% of the time right now, it's this setup. Under the coil, we have a condensate pan, and we have a condensate pan and line. Okay, so we have to get rid of the moisture off the coil. If we have an upflow air handler, it sort of is the same principle. Again, return plenum, air handler, supply plenum. We still have our indoor coil with the condensate pan and line. We have our blower, and we have our heat strips. Our filters someplace before the return plenum. Air movement is up. That's why it's called an upflow furnace or an upflow air handler. Now, you'll find in some mobile homes, in some pre-manufactured housing, might be a downflow system, but I'm not going to cover that here because it's the same basic principle. Just the air goes in a reverse pattern, and the return plenum is on the top, supply plenum is on the bottom. Now, what we really want to be talking about here is static pressures. That's the air pressure that is occurring inside the systems. Okay, on the return side of the system, everything is a negative. So we call it a negative pressure side of the system. Our neutral pressure, the point of pressure change, and again, this is air pressures, not refrigerant pressures, is going to be that blower. Okay, the blower is my point of pressure change. Everything on the outlet side of the blower is going to be a positive pressure. So our coil, condensate, filter, return plenum is all on the negative side of the system. Our heat strips, our supply plenum is all on the positive side of the system. Our point of pressure change, or the neutral pressure, is the blower. Again, in an upflow system, basically the same way. Okay, negative pressure on the return side of the system, blower neutral pressure, positive pressures on the supply side of the system. This becomes very important when we start talking about pressures. A static pressure is the outward pressure on an object. A static pressure does not include movement of air, or otherwise known as the velocity pressure. Static pressure in the United States is measured in inches of water column. Other countries that use the metric system have other measurements. You'll have to look those up. I'm not going into them here. An inch of water column is the amount of pressure that it takes to move water 1 inch vertically in a tube. It's written as 1 inch WC. Pressure is always a measurement of one location in comparison with another. So the pressure measurements you take of the ductwork is based on the pressure difference from the room you're standing in to the air pressure in the ductwork, plenum, or blower compartment. Pressure measurements will change based on where you take them. Filters have different pressure drops based on their cleanliness. A pressure drop is the difference in pressure before and after a component. Coils, your air conditioning coils, heaters, hot water coils, anything in the ductwork has a pressure drop. It changes the air pressure, and it's a resistance to movement, basically. So why does it all matter? You have to remember our magic number of airflow for air conditioning. We have to move 400 cubic feet per minute of air per ton of air conditioning. There's no option on this. This is the required airflow for air conditioning. So if we look at our air handler data plate, and I have whited some stuff out here just to protect people's privacy and make sure no one registers serial numbers that they shouldn't. You look at the data plate of the air handler. There's a lot of information on here that we use to calculate airflows. Okay, let me point out a few things. First of all, the model number includes the BTU of cooling a lot of times, but on some air handlers like this Rheem, it requires a trip to the manufacturer's website to look at the specification. Because this model number, RBHP, okay, 21, that just tells me the cabinet designation. It doesn't tell me the BTUs of cooling or the tons of cooling. Some air handlers, you'll have a 18, 24, 36, 30 in here, and that's actually telling you the tonnage of the system or the BTUs. Now, if I go to the Rheem website and pull up the specifications for this model number, I'm going to find a column for 21. So that cabinet that's referenced in my RBHP 21 has the ability to either be a 2.5 ton system or a 3 ton system. If it's a 2.5 ton, I'm looking for nominal heat and cooling CFMs, which is nominal means that's perfect. I'm looking for 1,000 CFMs. If it's a 3 ton system, we're looking for 1,200 CFMs. Okay, minimum would be 900 and 1080, but I don't want to deal with minimum. I always want to deal with nominal because systems do not get better with age. Okay, if I install a system or set a system up with minimums, it's only going to get worse as time goes on. The other thing you do have to look at is the minimum CFMs for the electric heat that's installed. If I go under 900 CFM, my electric heat strips are going to start overheating and it becomes a fire hazard. So always work with the nominal for the tonnage. Now, how do you know which size to use? Again, 2.5 or 3. Go look at the outdoor unit. Okay? Go look at the condenser or the outdoor unit of the heat pump. Also on the air handler data plate, there's a static pressure. Okay, on this air handler, it's a range, 0.1 to 1.0. That's a very wide range. Most often, you're going to find a single number, which is the maximum static pressure. Okay, a lot of times, 0.5 inches water column is standard. Okay, 0.3 is used on many air handlers with ECM motors and dehumidification. Most quality ductwork is based on 0.06 for the return and 0.1 for the supply, which gives me a 0.16 on the ductwork side. Okay, so again, look at the data plate to find out what our maximum static pressures are. And you shouldn't be at the max. Again, things do not get better with age. Okay, add the absolute values of the supply static and the return static together. Absolute values mean you ignore the positive or negative sign. Before you go any further, measure your static pressures. Make sure you zero the sensors before. Take a reading after the filter at the return side of the unit and a reading in the supply plenum someplace near the outlet of the air handler before any turns or takeoffs in the ductwork. Write these numbers down. Use your written down numbers to calculate the total external static pressure. Use that to go back to the air handler specifications and make sure that your static pressures are within the range allowed for the unit. ECM motors do not allow you to go beyond the specifications of the unit. That's a common misconception out there. ECM motors still have a range and still have specifications for you to be at. So here's an example. I have a negative 0.23 in my return. I have a 0.34 in my supply. You take these two numbers, drop the signs, and add them together. So I come up with a 0.57 inch water column total external static pressure. So if I use the specifications for the same unit I just did, I find the airflow performance data. 0.57 is someplace between 0.5 and 0.60, but here's the thing, I don't ever round down. So I'm going to go to 0.6. Okay, so if I am on 0.6, okay, and if I have a 2.5 ton unit, I'm going to have between 957 and 1013, okay, of my airflow. Now again, this means that my motor is at its basically highest speed, because from nominal, remember, I want 1,000. Anything else here is going to be too low. Granted, it's close, but it's still too low. If something changes, if a filter gets clogged, all of a sudden my static pressure, my airflow is going to be too low. If I'm on a 3-ton unit with that, okay, static pressure, I'm fine. Okay, because I'm going to be above that 1200, but I won't be too high. Okay, I'm going to be about 1264, but I'm not going to have too low of airflow. Okay, so 0.6 will work for both sizes. Do I want it for a 2.5 ton? Not really. I'd rather be 0.5 and under. Okay. Here's another example. Negative 0.53 and a 0.34. Add them together, I'm going to come up with a 0.87 inch water column total external static pressure. So all of a sudden I go over to my airflow performance. A 0.9, okay, which is what that will round to, is much too low for a 2.5 ton system, and it's too low for nominal for a 3-ton system. Remember, I need 1,000 or 1,200, okay? I'm too low. Okay, so all of a sudden you see where static pressure is affecting, okay, my airflow and my performance. Once I hit the max static pressure, it is so far out of range. If I go over that, I'm going to have major issues. That's why every unit has a maximum static pressure. It's for this exact reason. Reality check. The greater the static pressure, the lower the airflow. All air handlers and blowers have a maximum static pressure and a maximum airflow based on that static pressure. If you exceed the static pressure, you will not have enough airflow to properly cool and dehumidify the building. If you exceed the static pressure for heating, you take a risk of overheating the heat strips and the supply plenum. So let's talk a little bit about the causes of high return static pressure, because the return side of the system is where we have to start. On a balanced system, the return and the supply statics are within decimal points of each other's absolute values. If the return is significantly higher than the supply, there's a problem that is restricting the return airflow. So if I have like a 0.47 and a 0.13, I got to find the problem because my return static is too high. First step is to check the filters. Make sure there's only one filter installed in the system. Do not forget that a lot of systems are shipped with a filter in the inlet of the unit to protect the coil. Installers many times forget to remove these if they're putting in a return grill with a filter someplace else. Check and make sure you're working with a clean or relatively clean filter. Don't do diagnostics with dirty air filters. Okay, you got to have a clean filter. Okay, so if I have a clean filter and I still have the same values, okay, we have to realize, okay, a couple things on filters. Filters restrict airflow. The more the filter costs, the more it is designed to remove from the air, the more restrictive it is. A clean filter has a pressure drop. A dirty filter will increase that exponentially. Filters will not always be clean. They go in clean and they're designed to get dirty. Always give yourself a little leeway from the normal use of a filter. So this is a chart that actually shows the pressure drop for a 20 by 30 by 1 inch 3M filter. You'll see that there's different MERV ratings here. Okay? And the higher the MERV, the more the filter is going to capture. Okay, so if we're at a 3-ton unit, we want to have 1200 CFM of air. This is the solid blue vertical line that I've put here. Okay, it's roughly 1200 is where it's put. You'll see that based on the initial water, okay, based on a clean filter, okay, at 1200 CFM, I'm either going to have, for my lowest MERV filter, I'm going to have right over 0.15, so it's like 0.17. For my highest MERV filter, I'm going to have a 0.23 pressure drop. That's with the filter clean. Okay, so filters affect pressure drops. Again, a clean filter, if it's too tight, you're going to have a large pressure drop. If the system has return ductwork, find it and check it. Look for kinks in the flex duct. Look for collapsed ductwork. Finally, measure the ductwork. Rectangular, you need width times height. Round, you need diameter. Okay. Again, we have a 3-ton system, need 1200 CFM of air. And the ductwork we want to measure is my return ductwork, which is, oops, let me go back. This area to the left of the return plenum. Okay, you also want to look for restrictions. Okay, system uses flex ductwork. This is an example. Single run to a central filter. A 3-ton system requires 1200 CFM of air. Use a ductulator. It's an airflow calculation tool, and calculate the required ductwork at 0.06 inch water column. It's what I'd like to have for my return. If my return ductwork does not meet or exceed that size that comes up on the ductulator, your ductwork is the problem. Okay, so this is an example of the online ductulator. We have flex duct. Make sure you choose the correct type of duct. Okay, I want a friction rate of 0.06 per 100 feet. Okay, 100 feet. I'm going to use CFM, and I want 1200 CFM. You click the calculate button. I need a diameter of 18.5 inches, and my velocity is going to be 643, which, believe it or not, is a little bit high for a return filter. Okay, if you look at the specs of the filter, the velocity is probably closer to looking for a 300. So right there, I do have a problem. Okay. So my return ductwork at a minimum should be 18.5 inches diameter. There's a difference between flex, metal, and ductboard in airflow due to the smoothness of the interior surfaces. Metal will give you the best airflow, flex the worst. A hint, if the filter is sucking inwards, in other words, you see an air filter that is bowed inwards towards the air handler, and it is not dirty, you have a return ductwork issue. The ductwork's too small. It's trying to pull too much air through that filter. For rectangular ductwork, you have to convert it to round first. The same online tool will let you do this. Okay, you enter side 1 and side 2, find the equivalent round, 18.5. Okay, remember that 18.5 was the magic number. You'll never have 18.5 inch round ductwork. You'll go to 19 or 20. Okay, depending on what's available at the supply house. But if it's smaller than that, you have a problem. If you have a rectangular ductwork, you must use the interior size. That is where the air can flow. Ductboard can require you to subtract between 1 and 2 inches from the measurement of each side based on the thickness of the ductboard. Ductboard comes in 1 inch, 1.5 inch, and 2 inch widths. Plenums are often constructed with the thickest width. Way to solve a return static problem? Add a second return. Increase the size of the return ductwork. Use a lesser filter, even though I don't like that idea. Okay, because the better the filter, the cleaner the equipment's going to stay. If static on return is too low, go seal the leaks. Supply static pressure issues also exist. Supply static pressure can be too high or too low. High supply static means that there's not enough airflow moving through the system. It's going to cause you dehumidification and cooling problems. It is caused by improper duct sizing or duct restriction or possibly closed supply registers. If supply static pressure is too low, it's going to also cause problems with cooling and dehumidification. Make sure all the supply registers are open. Check the size of the supply ductwork main run. Make sure it can handle the CFMs of air required. Check for crushed, high static, or leaking, low static ductwork. Do not trust the technician that was there before you. Always measure again if you make any changes. Always document your changes and measurements. The best way to take your static pressure measurements is in cooling mode with a wet coil. Now, static pressures across the coil, especially if the coil's on the negative side of the system, can cause condensate issues. Any condensate connection on the negative side of the system must have a trap within 12 inches of the system for most newer air handlers. If you're unsure if there's a second trap, someplace like under a foundation or possibly a sagging line someplace, put an air brake tee right after the trap. Okay, so this is a condensate trap that is installed properly. You have a 2-inch minimum drop between the top of the trap and the air handler. Okay, you have to have 2 inches. That's required. Then your trap has to have a 3-inch minimum, okay, dip. That's under the 2 inches. So I have to have clearance of 5 inches here. Think about that when you're doing air handler installations. Now, if you think there might be a separate trap someplace in the system, you're going to come out of this trap, okay, and you're going to put an air brake tee, which is basically just a tee with a standing pipe in here, okay, that goes over the height of my air handler drain connection. Okay, it's just a T with a open pipe. What this does, it allows an air brake so you don't have a double trap situation. A double trap situation can back up water in here. A lot of installers use that excuse as the reason they do not install a trap at the air handler. Always install a trap at the air handler with an air brake if you have any doubt about proper pitch or anything else like that. If your static pressure on the return side of the system is too high, the velocity of the air across the coil could blow the water droplets off the coil into the blower compartment, causing a flood. If the static pressure is too high at the coil, the water can be sucked backwards out of the condensate line or pan, thus why we need a trap close to the unit. Note, you should have a condensate safety switch that will activate if the system is not draining properly. You don't want to cause a flood. For installs and changeouts, if you're upsizing a system that is part of a changeout, you must upsize the ductwork. You cannot put a 4-ton system in the place of a 3-ton system without having airflow issues. If you're downsizing a system as a part of a changeout, you can most likely use the existing ductwork at a lower static pressure. Static pressure issues go undiagnosed in about 85% of all service calls. Resolving static pressure problems can increase customer comfort, customer trust, and system performance. Identifying and resolving static pressure issues can increase profits. Measure. If you or your technicians are not taking static pressure readings on each and every service call, you're not doing the right thing for your customer. You must measure static pressures.